Hello everyone, this is Daniel Nunez with OneStopEnergies.com, and today we're going to do a test run of this double phase PoE mini generator. And what I mean by double phase is, as you can see, there's 6 magnets on this rotor and they're alternating north, south, north, south, north, south. Right? And right now what's happening is you have these 2 coils connected together in series, so that when these 2 coils are on, meaning when the magnet is positioned in the center of the coils, it fires this rotor and turns it. So as you can see, when these 2 are on, these 2 are off, and you can tell by the position of the magnets. So once this one kicks, once this pair kicks, this pair kicks after, and then so on and so on and so on, and it creates rotation on the rotor. So what we're going to look at today is we're looking at wall wattage. So we're powering the amplifier there. It's a normal home stereo amplifier. This is the sound frequency that we're going to put in, and we're going to start out at a low frequency and raise it up until the rotor loses synchronization. So it's going to get pretty noisy. We're going to start out at 12 Hertz and see what happens. So this is not the optimal configuration for this. We really wouldn't power this type of generator with an amplifier. We would use transistors and an advanced Hall sensor setup. But you know, this is just a test. So we started it up. It's 12 Hertz. See, we're pulling 215 watts. So that's a lot of wattage. And let's try to get that down by turning the shaft. Little rotation starts it up. So as it's spinning, you see that the wattage is going down. If you stop the spin, which it has a lot of torque, then the wattage goes back up again. So actually it's not going back up. Anyhow, so it does that at higher frequencies. But anyway, let's have a look. So started it up again, 208 watts, stopped it, still 208 watts. Anyway, let's get some faster frequencies there. That's 12 Hertz, 13, 14, 15, 16. Now we're at 20. So we're looking at 203 watts. 27 Hertz. Now we're at 200 watts. The faster we get that rotor spinning, the more the wattage is going to drop from the wall consumption. So now we're looking at 40 Hertz, 192 watts. This is 50 Hertz, 184 watts. And what's happening here is that I'm actually climbing the frequency rather quickly. We're already at 60 Hertz. So 60 Hertz is the frequency that conducts all the wall electricity. And that's 176 watts, 61 Hertz. So we're going to get this up over 100 Hertz. 70 Hertz, 170 watts. That's 80 Hertz, 160 watts. It sounds very beautiful, really smooth. And we're at 95 Hertz, 150 watts. And we're at 100 Hertz. 100 Hertz, we're pulling 147 watts now. So what I'm going to do is I'm going to start increasing it with smaller increments so that it doesn't lose synchronization. So I'm going to move over in the decimal range, and I'm going to tune it up like this from now on and see how high we could get it. It takes a little longer, but it's worth it, because what's happening is you can actually hear, as we increase the frequency, sometimes the generator, it has like a pausing or a pulsing that's happening when the rotor is trying to increase to the same frequency. So we're at 108 Hertz, 142 watts on the wall. And this is what I do when I check out the performance of these units. I'm basically checking for how high we can get this frequency and how we're sustaining the rotation on this magnetic shaft. So depending on the configuration of these coils, it's actually able to sustain a pulse at a higher frequency than if you were to wire it differently. So we're still increasing. 117 Hertz, 118 Hertz, 119, 120. So now this rotor is spinning at double the wall frequency, and that's 134 watts on the wall. So it's gone down significantly from 200. We could be generating power right now by wiring these slightly differently so that they're pulsing and picking up energy through the rotation and back EMF collapse. So every single time these coils collapse, they create a voltage spike of energy, and you could recollect that for battery charging, you know, running lights or running a motor. So this configuration will actually work with a DC motor. So we just rectify the energy and feed it into the motors. So it does work with inductive loads. I tested that out before. I want to fine tune it before I go ahead and give out anything that's worth replicating. But it's showing some stability here. So we're at 130. We're at 133 Hertz, 126 watts from the wall. So that's pretty fast. We're nearing 10,000 RPM. So you could do a Hertz to RPM conversion. Just go in your internet search and put in a frequency and check out Hertz to RPM. And you can actually see like this is going very fast. 140 Hertz. $120 watts from the wall. 142 Hertz. 144, and we're looking at 119 on the wall now. So I just heard something. When I got to 145, I heard that the rotor it had a pulsing. So what I have to do is I have to allow it to synchronize in whatever way it wants to synchronize, and then I'll continue tuning it back up again. That basically means that I have to increase the frequency at a slower speed. So we're nearing the point where this rotor is going to lose synchronization. We're at 147 Hertz, 148, 118 on the wall, wattage. And we're almost at 150. That's 150 Hertz. That's 152. Let's see if we could get up to 160. $154, 115 of wattage on the wall. So 156, 114 on the wall. So whenever we lose synchronization, we'll be able to see what happens to the wattage. And what normally happens is when we stop this rotor from spinning, that wattage is going to shoot right back up again. And we have arrived at 160. So we're pulsing at 160 hertz, 112 watts from the wall. Let's keep it going. So we're just going to push this to the limit and see how fast we can get this thing going. The wattage is still dropping. So that's like we're able to produce more electricity with a spinning magnet and still be able to lower the wattage on the wall. That's huge. So the generators of the future will be able to produce massive amounts of energy with very little lag. $166. So 167, we're looking at 108 watts on the wall. Alright, we're almost at 170. That's 170 hertz, 108 watts on the wall. So we had to allow the camera to cool down. We're back again, 171, 107 watts on the wall, 172 hertz, 173, 173 hertz there. Try to keep it in focus. Okay. It's 174. 106 watts. So we'll go ahead and do the conversion after this to find out exactly how fast this was going. That's 177. $178. Let's see if we can push it up to 180. Alright, 180 hertz. So again, those magnets are increasing in velocity every single time that I'm increasing the sound frequency, or I'm making the sound frequency faster. So it's very simple. There's an alternating current that's pulsing that magnetic shaft. And again, this is a dual phase generator. So for those of you who don't know, three-phase generators produce a large amount of today's energy. And if we could redesign the generators using these coils, we could effectively create much more efficient motor generators. Right now this is not generating any power, but it is demonstrating very high velocity and pretty stable torque. You know, not to mention this phenomena that the wattage just continues to decrease as we accelerate the rotor. So we're pushing 191. We're almost at 200 hertz, people. Let's see if we could get it up there. So the rotor is handling very well. Very smooth. $196. We're looking at 102 watts on the wall. Let's get it up to 200. $198. $199. $200. We're at 200 hertz, 102 watts on the wall, and we're still performing nicely there. Very smooth. That's 200 hertz. So let's keep it going. So right about now we should be approaching the speed of a propeller blade. So the airplane propellers, and we're only using dual phase. Essentially we can create a much bigger rotor and have multiple phases on this. So I'm talking about, you know, we can have 24 phases on this type of generator and be producing massive amounts of energy with massive torque. So we're at 108, 209 hertz, 104 watts on the wall. We're at 210 hertz. Again, we're going to do the conversion afterwards. Let's push it to the limit. If there is a breaking point, we're going to find out today. So 213, 214. That rotor is flying, people. And we just lost it at 215. So that's it. 215, and let's turn on this amplifier again. It just shut off on us. Let's see what that frequency normally consumes. Let's raise up the volume back to where it was. Okay, that's the max. And the frequency normally consumes 136 watts. But you saw that when we were spinning this magnetic shaft, we were driving it at 111. So that's the sound of the frequency that was pulsing it before. Where we lost it, you could hear the hum. And that's it. So that was the test. So again, this is a dual phase setup. So these two coils are firing, and then these two coils are firing, and there's an alternation. And this is ultimately the goal here. So we want to use this same type of setup with these batteries, have two interchanging batteries, so that this battery is driving these two coils and this battery is driving these two coils. They'll be alternating with each other. We could do that with a dual SEC circuit, so put an SEC on this right there and then like that, or an SEC on each circuit individually. So our aim is to achieve a pulsing circuit which can power lights and charge batteries in an alternating fashion, and we want to use the back EMF collapse to charge the opposing battery. So when this one collapses, it's charging this battery. When this one collapses, it's charging the opposite. So very simple concept, and thank you all for watching. Thank you for sharing your findings, and thank you for your support. One day at a time, we'll build the future coil by coil. Blessings and much love to you all.